Welcome to the session called HBK 3670 DAQ for Electroacoustics Testing. My name is Stéphane Giclet. I'm a principal engineer in the HBK Service and Solution team. I'm located in the French office close to Paris, France. Today's presentation will be dedicated to explain how you can easily develop your own electroacoustic testing application based on the 3670 DAQ. Thanks to the engine, you will be able to develop application in your preferred environment. In this session, I will start by quickly recalling what is the 3670 DAQ. Then, I will explain what is the engine toolbox we developed for this device and the philosophy behind. I will describe its architecture and show how to use it. We'll go through different examples in MATLAB and Python environment to illustrate how it works and how easy it is to use the 3670 DAQ for electroacoustic testing. Finally, we'll end with a Q&A session where you will be able to ask your question. The 3670 is a data acquisition system specifically designed to be used with CCLD measurement transducers that digitize and streams data through a USB 2 interface. It goes up to 96 kHz sampling frequency. You will find inside 24 bits analog to digital and digital to analog converters. The driver is ASIO compatible, it means low latency driver. The CCLD switch can be set individually on each input channel. The device is rugged, light, IP50 and no fan inside. It means silent operation. The E-Engine Toolbox is a functional library dedicated to the 3670 DAQ. It is intended as a toolbox of complete electroacoustic tests designed to be driven from user-defined third-party software. It's easy to use and compatible with the most common development platform like MATLAB, Python, or Visual Studio. No need for specific signal processing or advanced development skills. Everything is already included in it. You can do I/O calibration, equalization, random, sweep sign, step sign, waveform streaming test. You can do time data recording. All the functionalities that are mandatory to do frequency analysis or distortion like THD or Raman bus calculation, for example, are already included in it. The measurement parameters are controlled by values stored in dedicated XML file on the host computer, and they can be edited manually in a text editor or programmatically from a user-defined application. Results are available in different file formats like XML, CSV, MATLAB, or WAV and HDF5 for time data recording. You can control input and output very easily from a user-defined test control and analysis software. The E-Engine is a .NET development in C#. No need to install any runtime. The .NET framework, installed by default with Windows, is providing all the necessary dependencies. So the package is light and optimized. I think it's around 30 megabytes for the installation. It is based on a signal processing library that works in the same way as all the other HBK sound and vibration portfolio application run. Two components are embedded in the toolbox. The executable itself that can be called directly in command line mode with arguments, and one library that can be referenced in your development environment. This last one offers more interactivity capabilities during measurement and processing. There is a set of configuration files in XML file format that are available. If we look at some of them, you will see that, for example, for the engine setting.xml file, this one contains information about data storing folder. This one is specific for command line mode. It's just to precise if we want to have a press enter request or not in the end of a sequence. A settling time option in seconds is available. we can precise if we want to integrate or differentiate signals. So it concerns essentially vibration signals, vibration measurement like displacement, velocity, or acceleration, and a calibration threshold value that can be used to check if the calibration ran fine or not. Some other XML files are available, like the detected device file. This one is automatically updated when we ask to detect potential device connected to the hardware. So for example, in this one, you will see that it has detected one device. The selected device capabilities. So for the device that has been selected, you will get all the information regarding its characteristics like input latency, buffer size, sample rate. You have a configuration file for input channels. So these one are also automatically created the first time you connect and you select a specific device. So here 8 channels, where you will find some information like name, if this channel is active or not, its associated reference channel, sensitivity, calibration information, dB reference, latency, etc. etc. The same thing is available for the output channels. So in my case, 2 output channels are available, where you will find also information like name, if this channel is active or not, sensitivity, calibration information. Some supplementary information is available for the outputs, like the signal type we are going to associate to a given channel. So it supports white, pink, fixed sign, swept sign, step sign, and waveform streaming. And depending of this option, the software will know where it will have to take the corresponding parameter, the corresponding settings. For example, for a sweep sign, it will go here to know what's the level of the sweep sign, what's the start and frequency, the sweep mode, the sweep time. If we ask for repetition, if we want to insert silent between different sweeps, the fade mode, and fade in and fade out duration at the beginning and the end of the sweep. That's the same for the other, but with specific settings. If we look, for example, at the calibration setting file, this is where you will be able to define the reference frequency, reference level, reference unit, so you can run in dB or engineering unit, the duration, the file format of the output file, and here if we want to calculate THD and what are the harmonics to use for the THD calculation. And as for calibration we run with an FFT analyzer, you have a section dedicated to the FFT settings, like the sampling frequency, frequency line, block size, averaging type, number of average. Some parameters in fact are linked together and updated automatically by the engine behind the scene. Here the reference waiting window, the response waiting window. So for example, for calibration by default it's put in flat top, etc. etc. If I look at one of the test settings, and for example the sweep sign, here you will find the measurement mode you would like to run. So it supports spectra, phase sign spectra, FRF, and CPB, the duration of the test, the name of the file that will be created containing the results, if we want to measure and remove extra latency based on the physical distance between the source and the transducers, the file format of the results, if we want to apply equalization during the test, if we want to do a recording in parallel with the test. Depending of the measurement mode, the software will know where to take the complementary settings. For spectra, phase, sign spectra, and FRF, we run with an FFT analyzer. So here you will be able to set up all the settings for the FFT analysis. If we run with, if we ask, for a CPB, then you will be able to adjust the CPB settings in this section. If we ask for synthesize CPB, it will be in this section. And if we ask for time data recording in parallel, you will have to adjust the settings in this section. So the philosophy is the same for all the other tests. A complete user's manual detailing the configuration file and the arguments supported to run a certain task is also available. And for those who want to use the e-engine as a library, there's a programming documentation detailing all the content of the library that is also available. So for example, I go on one of the main class, the engine, I have access to all the methods that are available in the library to do different tasks like get input channels, get output channels, set FFT settings. All the methods are available. On the architecture side, you will have two different components. So the one named program, so this is the executable, and this one doesn't expose any property, any method, because we'll run it through a command line with arguments. And the other one corresponding to the API that contains all the different properties, methods, events necessary to interact with the e-engine. Here you have all the different other classes that are available. One dedicated, for example, we talk about the application. Sorry, I will move it here, where we can find all the properties I've described in the XML file, like data folder, set link time, integrate, differentiate, option, calibration threshold, and that's the same for all the other. So in terms of architecture, you have class for all the different settings. You have some ones dedicated to the device, one dedicated to the input channel, another one to the output channels with more functionalities like the settings dedicated to the random, fixed sign, sweep sign, step sign setup, etc., etc. Here you will find all the events, because some notifications are supported, and you will be able during programming to catch these events, to interact and to synchronize your application with the e-engine execution. Some other are also available, and some here are essentially for internal usage. The e-engine can be used directly in command line mode. No need for any other software. Just a text editor to manipulate the configuration files. For example, in a command prompt, I can call the e-engine program with some arguments. It returns the e-engine version number and asks to press OK to exit, to press enter to exit. If I change in the engine settings, press enter from true to false, and I will save it, then no need to press enter to exit to leave the execution of the program. So you can see the interaction between the configuration files and the execution of the e-engine. Now, if I want to detect the available devices connected to my computer, I use the detect device argument. One device has been detected. I can then select device number 1 corresponding to this index, and I need to use a third argument, true or false, just to precise that I don't want to overwrite the existing input channels and output channels setting files. The first device has been selected. I can recover information about its characteristics like sample rates, buffer size, input and output latencies. In the file, you can see that all these files have been updated, not the input channels because I didn't ask to update it. Now I would like to do a calibration of the first input where I have connected one 4944 microphone. In the calibration settings, I just check the reference level, reference frequency, reference unit, test duration, and the result file, and precise some supplementary option if I want to calculate THD or not. Then I will ask to calibrate input channel 1. The calibration settings are just recalled, just for information. The calibration ran 5 seconds, a new sensitivity has been calculated, and it is displayed. And if I switched to the input channel, yes, this information has been automatically updated in the file. If I want to change the calibration settings, for example, I would like to do a 10-second calibration, I would like to calculate THD at the same time, I just have to change this setting and run it again. So you can see that now duration of the calibration is 10 seconds and THD calculation has been asked with harmonics 1, 2, 3. It's done. So you can see how easy it is, in fact, to develop your own application in command line mode. All the development environment that supports shell execution are potentially supported. For those who followed the previous session animated by Vince Ray, you've already seen some example in VBNet. He used the E-engine in command line mode to, with a process object in his demonstrator. Another way to work with the E-engine, more advanced, is the API mode. With this one, in fact, we are going to use the E-engine not as a program, but as a library. And all the development environment that supports .NET assemblies, because the E-engine has been developed with the .NET framework, are supported. It includes MATLAB, Python, Visual Studio, of course, and LabVIEW, for example. So the majority of the most popular development platform can be used in association with the E-engine. In the next minute, we'll focus on how to use it in a MATLAB environment. Then we'll do the same in a Python environment. We'll spend the next minutes on the MATLAB environment, and I will show you how to interact with the E-engine and how you will be able to build your own dedicated programs to perform electroacoustic testing. MATLAB supports by default .NET assemblies, so it's very easy to use some .NET libraries directly in your MATLAB program. So how to start? I will start my script by cleaning all the environment, and then I will need to define some variables that will be used to add the assembly and declare and instantiate our E-engine. So I've already prepared some piece of code. I will copy paste everything. So one first variable containing the path to the installation folder, and a second one containing the complete name of the executable. And this one is needed to add the .NET assembly in our environment, and it will be called EEngine. We import all the EEngine namespace just for development simplification, to avoid to have to write every time EEngine dot something to access to a specific class of object. Then we declare and instantiate our engine object by creating a new engine, and we need to put in arguments the installation path for internal needs. And that's all. So it means that every time you will use the EEngine in a MATLAB script or MATLAB program, you will have to do this part. So now I have access to the EEngine object and I can start to interact with it. For example, if I want to get the version, as what we have seen in command line, I call the getVersion method of my engine object. If I run the program, I get the results. I of course can do more, for example, like getting the EEngine settings by calling the getEngineSettings method. And that's where in fact the programming documentation shown previously is really useful to help you to understand what are the methods and how to use them. There is also some error management in the library. It means that every time I run or I call a method, an error message property is set, and if it's not empty, then I will have to manage the error. If I run this one, I get still the version, okay, but I set an engine setting object with the engine settings information. If I want to list this information, I have directly access to the engine properties. So I can see here that in my EEngine settings file, the data folder, this is where all the results will be stored, is this one: settling time 0, integrate differentiate 0, calibration threshold 10 milli. There are some other methods available also to interact with the setting files. There is a set engine settings method where you will be able to update these properties. Same thing for the device detection. There is a detect device method where you will recover all the detected device, etc., etc. So in my example, for example, I will show you the complete file. So that's an example file to adjust some settings. If I launch it, I will be able to execute different kind of things, and you will see that, okay, I got the settings, I detected the device, I have the list of detected device. Once the first one has been detected, so we can see that its selected property has been changed from false to true, and I have the selected device capabilities. And beside, I've created also some object for random settings, output channels, input channels, etc. So I can manipulate them directly in MATLAB, modify them, and set them again to update the configuration files. So some different examples have been prepared, and for example, if we start with the calibration, in this one you can see all the parts corresponding to the engine declaration and instantiation. For this one, I will come back just a little bit later. I set the calibration setting, 1 kHz, 94 dB. I will ask for 5 seconds. The results file will be XML, for example, in this case. Do I want to do some THD calculation? What are the THD harmonics to take for the THD calculation, and what's the block size to use for the calibration goes behind? That's the FFT running. And then arguments are this one, so the same as the one used in command line mode, but instead of working in command line, I will call the execute method of the engine and associate the arguments. So what about these parts and this one? In fact, the e-engine library contains also events notification. They are here, here, and here. So different notifications are available. And what we are going to do is adding listener for the .NET object. So here that's our engine. In this case, we are going to track feedback event, calibration results updated, and calibration results available. And once we have defined them, we can execute the task, and once the task is finished, we are going to delete them again because we don't need them anymore. And we'll see how it works. You can see that here I have some feedback, and here I have some displays in real time. So I will repeat again just to show you. So this information is associated to the feedback event, so everything that is displayed in the command window. The part corresponding to the calibration results update, it's when I want to update the display, and the one corresponding to calibration results available, and I can, for example, comment it for the moment. Are the one corresponding to display the results when all the final results are available. So in this case, it just displayed the last updated information. And how it works? In fact, that's specific to MATLAB. We are going to add a listener to the engine corresponding to this notification, so the feedback, and we are going to call the feedback function, and the feedback function is stored here. So I already prepared it, and the feedback is just getting some event information, so a message type, a message itself, and print it to the screen. So you can see the keyword start, setup, measure, process, result, end correspond to the message type, and the message itself is what is following. So you can completely interact with the e-engine during its execution, displaying some useful information, and you can filter based on the message type. If there is an error, for example, there is also an error keyword, I would like to perform a specific thing. Or if you want to split, the measure information will go somewhere, the process information will go somewhere else, the results has to go here, etc. You can do that. Same thing with calibration results update. In fact, this script contains the code that has to be executed when the calibration results update event is fired. And it means that during the measurement, every time a new average in the FFT processing will be done, the MATLAB will execute this part. So this part contains essentially display features. So I've built a small, very simple program that is performing input channel calibration on the 3670. No need for more things under MATLAB. So we propose some other examples to do output channel calibration, output channel equalization, perform some tests like random noise, step sign, sweep sign, etc., etc., etc. If I want to do a more to develop a more advanced application, of course, I will go to the design app. I've already prepared something to create my graphical user interface. I put a button, I put a log area where I want to display information during the execution of the task, and I put some displays where I would like to display the data during the calibration. In the code view, main part of this one is automatically created by the app designer. And here, in fact, I've just created a callback corresponding to the button pushed event. And that's where I've put declaration, instantiation of the engine, add the listener I wanted to use, so exactly something similar to what I've done in the script directly. Set the calibration settings, define the argument to calibrate input channel 1, execute the task, and then removing the listener in the end. And you can see that the only difference regarding the listener, I don't call directly the script I shown for feedback and calibration results, but I call the one that are stored in the app itself, so in this file. And they are here, I've created them here, and they are a little bit different because instead of displaying information in the command window, we are going to display feedback information in the log text area, and the same for measurement update. Instead of displaying a new figure with new plots, we are going to update the axes objects that are in our interface. If I want to run, it's here, and I would like to do calibration. So you can see execution of the program, it's calibrating, information about the execution, and everything is finished. So really easy to interact with the engine under MATLAB, and you can imagine to develop your own dedicated application. No need for any other toolbox to do that, only connecting to the engine. We leave MATLAB now to switch to Python environment, where I will show you how to interact with the engine. Python supports .NET assembly with the help of PythonNet package. You'll see that the way to interact with the engine is really similar to how it works under MATLAB. I will first import some package libraries. One specific command to Python, this one, and I will just explain just a little bit later, and defining one installation path variable, adding a reference with the help of the CLR to the e-engine, importing the assembler. This one is mandatory to force Python to run the engine in single thread, and it's necessary for the audio driver. That's not the case in MATLAB, because MATLAB is running by default in single thread mode. We declare and instantiate our new engine object, and we run a command to get the version. If I run the program, I get the version. Of course, we can do more, like I will comment this line, for example, getting the engine settings, checking if everything ran fine to recover the information, and displaying the information in engine settings, data folder, settling time, etc., etc. A more complete example file has been created to show how to play with the detect device, the select device command, the input channels, how to get them, how to set them, the output channels, how to get them, how to set them, etc., etc. And a small example in the end concerning the output channels random settings. Some other examples have been written to show how to perform some specific task. For example, the input channel calibration. I will run one, and you will see that everything's run. 5 seconds calibration. The result is displayed in the end, and the new sensitivity has been calculated and updated in the file. And if we look a little bit more in this file, we'll see that, oh, the beginning is exactly the same, always, always, always. Here we import some functions. I will talk about them just a little bit later from external files. They are here, feedback, calibration results, updated and validate. We declare and instantiate our engine. We add the handlers for the .NET object. It means that we want to follow notification of the engine, and when we'll reach this, so this notification will be fired, this event will be fired, we'll execute the content of these functions. We define calibration settings, and we attach calibration settings to the engine. Then we execute the input channel 1 calibration. And once finished, we remove the handler we used. The handler, for example, feedback, is just printing the arguments of this event on the screen. So it contains this information: start, setup, etc., etc. Calibration results available is just displaying some information. Current time elapsed, and this one is updated during the execution. And calibration results available is just displaying some results in a plot. So, accepting some specificities based on the platform we are using, the rest is exactly the same. So we have performed input channel calibration. I've created some other example for some other tests, like random noise test, sweep sign test, step sign test, waveform streaming test. And I will finish with a more advanced example, this one, that contains also a graphical user interface. In this one, so I've created some different tasks. The first one concerns the setup, so I would like to detect the device. I get not in outputs directly, but in my user interface, the detected device. I use the selected device, so I select this line and I use it, and I getting automatically all the associated input channels and output channels. I can set up, okay, I will go back to the default sensitivity of this channel. I save it. And then I will go to input channel calibration. Again, but I promise that's the last time. Here you can create, so set up the settings directly, adjust the settings directly in the user interface. For example, I would like to work with 1 Pascal RMS instead of 94 dB. Duration, do I want to calculate THD? The block size, the results file format. And if I press calibrate, you can see that, okay, it's a little bit more advanced program because I have some real-time display of the time response, the average auto spectrum, the updated information during the processing, and in this log window, all the different feedback coming from the engine. The sensitivity has been updated, calculated, and if I go here and use selected device again to update my table, you can see that the sensitivity has been adjusted automatically in the file. So we have finished with input channel calibration. We'll go now on some other tests. So I will move my microphone just in front of my mouse simulator, and I will do some other tests to illustrate how we can use the EA engine. So random noise test, I will be able to do white or pink excitation and defining its settings. The test settings, spectra, FRF, CPB, so I put this kind of option in my GUI. If I want to remove latencies, apply equalization, choose the result format, the FFT settings I would like to use, averaging mode, reference weighting and response weighting window, etc., etc. So you can imagine to put all the different options that are available in the XML file to read and write this information directly through the user interface. The last one concerns CPB. If I ask to do CPB, where I will choose the nth octave option, start frequency, stop frequency, and the averaging characteristics. So we'll start with spectra, for example. In my setup, I had 2 channels, input channels activated. This one is directly connected indirect to the output. This one has my microphone, this one is my simulator. I will do a test with white noise. Is it too much? Perhaps. And you can see that in this one I've added also feedback during data recording. So you have directly the trace of the time data recording, and here just after the results, so the FFT processing. So here we have the average spectra of the output, the input 1, so it's our microphone, and input 5, this is the channel connected directly to the output. So hopefully we have the same result. I can switch to FRF, for example, rerun the test, and then behind the scene in my program I asked to display the average FRF this time. So here we have the average FRF, so the response of the microphone regarding the excitation signal, and here of course one constant level of input 5 that is directly connected to the mouse simulator. If I switch to CPB, I get the CPB auto power, so spectra of the different channels. You can see the slope on the CPB, of the white excitation signal. If I switch to pink, it's then flat. Last example, step sign test, where I'm going to do a step sign at this level between this frequency, this one with a R80 resolution, 12 minimum cycles, or 10 milliseconds mean duration for each cycle, for each step, sorry. Measurement mode, spectra or FRF, distortion information. Okay, I run it. And automatically the processing is not an FFT1, it's a little bit different, it's kind of harmonic filtering. You have seen that the harmonic spectra were updated online during processing, and in the end we get the final results corresponding to the average FRFs. So it's just to illustrate how we can use the HE engine in MATLAB or Python to build our own dedicated application. I hope you enjoyed this session and that it helped you to understand better what are the capabilities of the 3670 DAQ and the HE engine to develop your own dedicated electroacoustic application. You have seen that the HE engine contains all the essential functionalities required for electroacoustic testing. Quality and accuracy of measurements and results are guaranteed. It's a really light and optimized toolbox, no runtime is necessary. It's flexible because you can use it in command line mode or in library mode in different development environment. And we can provide also services to help you to build your own application. It's time now for the Q&A session. Please feel free to ask me your question. Thank you.